Imagine you're standing in the middle of a massive industrial plant.
Okay.
You've got steam boilers hissing. You have chemical reactants flowing through miles of pipe, hydraulic systems lifting tons of weight. It's a beast of a machine.
Right.
But here is the terrifying question. How do you know the beast isn't about to have a heart attack?
You have to check its pulse.
Exactly. You have to check its pulse.
That's a great way to frame it. And in the industrial world, that pulse check is the pressure gauge. It is, arguably the most ubiquitous critical instrument in any facility.
Right.
If a temperature sensor fails, you might, burn a batch of cookies. If a pressure gauge fails, or worse, if it lies to you, you could be looking at a catastrophic pipe burst.
Or an explosion.
And
we see these little dials everywhere. On fire extinguishers, on bike pumps, on these, massive oil refinery stacks. They just look like simple clocks with one hand.
They do.
But today, on this deep dive, we're going to look inside that metal casing because, as it turns out, there is no microchip in there. It's pure mechanical engineering.
Exactly. We are analyzing a technical training module for instrument technicians, specifically Module 310103C.
Okay.
And the mission today is to understand the surprisingly complex clockwork that translates an invisible force pressure into that moving needle you rely on.
And the best place to start is with the aha moment from the source material. It uses an analogy that I have to say I haven't thought about since I was a kid at a birthday party.
I know which one you mean.
The source basically says that high-end industrial safety gear works on the exact same principle as a party streamer.
It sounds ridiculous, but physically it's completely accurate. The mechanism is identical.
Okay, let's unpack this.
Yeah.
You know those paper party favors? The ones that are rolled up tight, and when you blow into the mouthpiece, they just whoosh, uncoil and straighten out.
Right. That is the fundamental mechanism of the most common pressure gauge in the world.
Yep.
The boredom tube.
But I want to understand the physics here. When I blow into the party streamer, air pressure goes in. Why does it straighten out? Why doesn't it just sort of, balloon up or explode?
It all comes down to geometry and surface area. So think about that curved paper tube. You have the inside track of the curve and the outside track.
Okay.
The surface area on the outside of the curve is physically larger than the surface area on the inside.
Okay, that makes sense. The outer wall is just longer.
Precisely. Now remember that pressure equals force divided by area. So if you pressurize the inside, the pressure is the same everywhere.
Right.
But because there is more area on that outside curve, there is more total force pushing against that outer wall than the inner wall.
So it's a force imbalance.
Yeah.
The outer wall is being pushed harder than the inner wall.
Exactly. That net force pushes the tube outward, trying to straighten it into a line. And that movement, that uncoiling, that is what we measure.
So the boredom tube is the muscle of the gauge. But the source material gets really specific here. It's not just a tube. In the real world, this is a metal tube, flattened out and bent into a specific shape.
Right.
And apparently, the shape really defines the personality of the gauge.
It does. It absolutely does. The source outlines 3 main designs: the C-shape, the spiral, and the helix.
Let's start with the C-shape. It sounds like the standard vanilla version.
It is. It's simple. It's cheap to manufacture. It looks exactly like the letter C. But mechanically, it has a limitation.
Which is?
Because the tube is relatively short, just one curve. The tip doesn't move very much when you pressurize it. We're talking millimeters.
That seems like a problem if you want the needle on the dial to sweep a full 270 degrees. You'd have to magnify that movement significantly.
You need a transmission, a gear system with a high amplification ratio. And just like in a car or a bike, high gearing introduces issues.
More friction.
More friction, more backlash, more potential for wear, more error.
So if you want accuracy, you want the tube to do more of the work itself so the gears don't have to.
Exactly. That's where the spiral and helix shapes come in.
These are the ones that look like a coiled snake or a spring.
Yes. A spiral is coiled flat, like a rope on a deck. A helix is coiled vertically, like a spring.
And the advantage here is just length.
It's length. You have much more tube effectively wrapped up in there. More tube means more uncoiling.
So the tip moves further.
Much further. And because the tip moves a significant distance, you don't need as much gear amplification to move the needle. That makes them inherently more accurate and sensitive, especially for lower pressures.
The source mentioned a specific detail about the spiral versus the helix that caught my eye. It seems like the spiral is kind of falling out of fashion for heavy-duty work.
That's an important nuance. Think about a flat spiral. The coils on the outside have a much larger radius than the coils on the inside.
Fair.
That means the stress isn't distributed evenly. The largest bending stress happens at the outer coils.
So it has a built-in weak point.
Right. Over time, that concentration of stress leads to failure. The helical design, on the other hand, because every coil is the same size, it distributes that stress evenly along the entire length of the tube.
So it's stronger.
It has largely replaced the spiral in modern heavy-duty applications because it just lasts longer.
Now, we've talked about the curve of the tube, but the source also dives into the cross-section. You mentioned earlier that the tube has to be flattened. If it were a perfect circle, the pressure would push equally in all directions and it wouldn't uncoil, right?
Correct. It has to be non-circular to want to straighten out. The source lists 3 main cross-sections: pointed oval, flat oval, and flat arch.
This feels like a Goldilocks situation. You have to pick just the right one.
Think of it as a trade-off between sensitivity and strength. The pointed oval is very narrow, it's extremely sensitive, it wants to round out very badly, so it gives you a lot of movement.
Great for low pressure.
Yes, typically under 160 kilopascals. But because those edges are sharp-pointed stress concentrates there, it has a shorter life, it's fragile.
So if I'm running a high-pressure hydraulic line, I definitely do not want a pointed oval.
Definitely not. You'd want the flat arch or circular cross-section. The source calls this one the strongest. It's almost round already.
Okay.
It's used for pressures of 6 megapascals and up. It's a tank. But the trade-off is sensitivity. It barely moves.
So for the flat arch, you're back to needing that high gear amplification.
You are.
And the flat oval is the middle ground.
Exactly. The industry workhorse. Good balance of movement and strength.
This brings us to a really critical concept that the source emphasized. We're bending metal here. And anyone who has bent a paperclip back and forth knows that eventually metal gets tired and breaks.
This is the concept of elasticity and fatigue. We are asking this Borden tube to act like a spring. We want it to deflect when pressurized and return to exactly 0 when the pressure is gone.
The source has this chart, a pressure displacement curve, and it marks a very scary spot called point A.
Point A is the yield point. If you overpressure the gauge past point A, the metal stretches permanently. It's like pulling a slinky too far.
It won't go back to its original shape.
And if that happens, your gauge is ruined. It'll never read 0 again. But here's where it gets really interesting for anyone operating this equipment. The source makes a huge distinction between static loading and dynamic loading.
This is crucial. Static loading is when the pressure changes slowly. So think of filling a tank gradually. In that case, you can safely use the gauge right up to its full-scale point B on the chart.
Okay, so if the dial says 100 psi and I increase pressure slowly, I can go to 100 psi.
Yes. But dynamic loading is when the pressure fluctuates rapidly, pulsing, vibrating, jumping up and down.
I see.
If you are in a dynamic situation, the source says you must never exceed 90% of the static limit.
Why the 10% buffer?
Metal fatigue.
Sure.
Every single time that tube flexes, it uses up a tiny bit of its life. The industry standard goal is a lifetime of 200,000 load cycles.
Wow.
If you push a dynamic load to the limit, you will snap that tube way before you hit 200,000 cycles. And 200,000 cycles sounds like a lot, but if you have a pump vibrating at 60 times a second, that happens in, what, under an hour?
Exactly. You could destroy a brand new gauge in a single shift if you don't respect the dynamic loading limit.
So we've covered the Borden tube, which is great for higher pressures. But the source material shifts gears to talk about loop pressure, like measuring the water level in an open tank.
Right.
A Borden tube is essentially a thick metal pipe. A few inches of water isn't going to uncoil it, is it?
No, it would be like trying to measure a breeze with a brick. It wouldn't register. For low pressures, we need something much more flexible. We move away from tubes and toward diaphragms.
The diaphragm seems pretty straightforward. It's a metal disc held at the edges. Pressure pushes on one side, and the center bows out.
Simple concept, but the execution has some clever engineering. If you just use a flat sheet of metal, the movement isn't linear.
Okay.
It resists more the further it stretches. So manufacturers stamp convolutions into the metal.
These are the ripples, right? Like dropping a pebble in a pond.
Exactly. Those concentric circles allow the metal to unfold slightly rather than just stretching. It makes the displacement proportional to the pressure, which is what you need for an accurate reading.
The source also mentions that diaphragms are intrinsically safer than Borden tubes in some ways. Why is that?
It's because of how they can be supported. Imagine a Borden tube. If you overpressure it, it just balloons out until it bursts.
Right.
But with a diaphragm, you can put a solid metal backing behind it. They call it a diaphragm bed.
Oh, I see. So the diaphragm stretches until it hits the wall behind it, and then it literally can't stretch anymore.
Right. It flattens against the bed. You can overpressure it significantly, and it won't yield because the bed stops it from moving past its elastic limit.
Now, what if a single diaphragm isn't enough? What if we need to measure really tiny pressures,
Then we use a capsule.
which is essentially two diaphragms welded together at the edges like a hollow pancake?
Hollow pancake is a good visual.
Mm-hmm.
By welding two together, you double the expansion for the same pressure. Both sides bow out.
I get it.
This allows you to measure very low pressures without having to make the metal dangerously thin.
And if that's not enough, the source shows a bellows, which looks exactly like an accordion.
The bellows is fantastic for maximizing movement in a small space. It's a thin-walled cylinder with deep corrugations. You get a lot of travel expansion and contraction for very low pressures, typically 0 to 10 psi.
Okay, so we have our sensors, we have the Borden tube uncoiling, the diaphragm bowing, the bellows expanding. But that movement is tiny. We're talking millimeters.
Tiny.
How do we turn a 2-millimeter bulge into a needle sweeping across a dial so I can read it from 5 feet away?
This is the movement. It's the brain of the operation. It's a tiny clockwork mechanism inside the casing.
The diagram in the source shows a system of levers and gears.
Right. The tube tip pulls a link. That link pulls a toothed segment. Basically a gear that's only a slice of a circle.
Like a quarter circle.
Usually about a quarter of a circle, yeah. That segment turns a tiny pinion gear attached to the needle.
That's just leverage.
Yeah.
A small pull on the lever creates a big spin on the gear.
Precisely. But anytime you have gears with teeth, you have a problem called backlash.
Backlash.
There's a tiny gap between the teeth. If the pressure drops slightly, the needle might wobble or not move immediately because of that gap.
So how do they fix that?
A hairspring. It's a tiny coiled spring, just like in a watch, that keeps constant tension on the gears. It ensures the teeth are always touching on one side, eliminating that play.
Now, here is where it gets really interesting for the people who actually have to maintain these things. The source goes into detail about calibration. Basically, what do you do when the gauge is lying to you?
There are three main types of errors the source discusses: zero error, span error, and angularity.
Zero error seems the most obvious. There's no pressure, but the needle is pointing at 5 psi.
Right. The fix is usually simple. You either rotate the dial face itself, or, on some gauges, there's a microscrew on the pointer arm to physically move the needle back to zero.
Span error sounds trickier.
Span error is when the needle moves, but not at the right rate. So you go from 0 to 100 psi, but the needle only moves from 0 to 90.
So the span of travel is too short.
It's too short. The gauge is lazy. It's not moving enough for the pressure applied.
And how do you fix that? You can't just move the needle, because then the zero will be off.
You have to change the leverage. Inside the movement, there's a control point where the connecting link attaches to the gear segment. If you slide that connection point further out or closer in, you change the mechanical advantage.
It's like sliding your hand up or down a wrench handle to get more torque.
Exactly. Moving that point changes how much the gear turns for every millimeter the tube moves. It's a fiddly process. You adjust the span, then check the zero, then adjust the span again.
And then there's angularity.
That's a linearity issue. Maybe it's accurate at 0 and 100, but at 50 psi, it's reading 55.
Oh, okay.
That usually involves adjusting the length of the connecting rod itself. You are physically altering the geometry of the triangle to straighten out the response curve.
There is one more calibration factor that implies these things are smarter than they look. Temperature.
Ah, yes. Metal expands when it gets hot. If the Borden tube heats up, its elasticity changes, its Young's modulus shifts, it gets slightly softer, and the metal linkage expands.
So it causes errors?
It causes measuring errors, yes.
So if I have a gauge on a steam line, it's going to read differently than if it's on a cold water line just because of the heat.
Potentially, yes. That's why high-quality gauges have temperature compensation. They actually build a bimetal strip into the linkage.
A bimetal strip that's two metals stuck together that expand at different rates, so it curls when it gets hot.
Exactly. As a gauge heats up and the reading starts to drift, the bimetal strip curls and effectively shortens the lever arm just enough to cancel out the error. It's a mechanical autocorrect.
That is incredibly clever. It's a mechanical computer performing a subtraction calculation using thermal expansion.
It really is.
So we've built this delicate, high-precision instrument. We've calibrated it. Now let's talk about how to keep it from dying. because industrial environments are brutal.
They are. Vibration is the biggest enemy. We talked about fatigue in the tube, but vibration also destroys the gears. If you mount a gauge on a vibrating compressor, that needle is going to shake so fast it will look like a blur.
You can't even read it.
You can't read it. And worse, the source says that vibration can cause resonance-induced fracturing. The tube can actually shake itself apart.
So what's the fix?
This is why you see gauges filled with liquid, usually glycerin or silicone oil.
I always thought that was just to keep the glass from fogging up or something.
Well, it does keep corrosive air out, but the main purpose is damping. The oil is thick. It acts like a shock absorber for the moving parts. It stops the needle from jittering so you can take a reading, and it lubricates the tiny gears so they don't grind themselves to dust.
So the oil is a dashboard damper.
Nice. It also prevents condensation and ice formation if the gauge is outside in freezing weather.
Finally, let's talk installation. The source implies that a lot of people just screw the gauge into the hole and walk away. But there are rules.
There are always rules. First, you need a shutoff valve. You have to be able to isolate the gauge to replace it without shutting down the whole plant.
That makes sense.
But here's one that trips people up. Height. If the gauge is mounted higher or lower than the actual pressure tapping point and the line is full of liquid, you have a head pressure error.
Because the weight of the fluid in the tube pushing down on the gauge adds extra pressure.
Exactly. Imagine a 10-meter tube filled with water leading down to a gauge. That column of water exerts about 1 bar, almost 15 psi of pressure just by sitting there.
Wow.
So your gauge reads the process pressure plus 15 psi. You have to account for that.
And the final installation tip, and this one is gross but important, the dead space.
Yes. The tube leading to the gauge is a dead end. Fluid goes in, but it doesn't flow through. It just sits there.
And the source warns about decomposition and deposits.
Sludge, sediment. If you are measuring dirty water or crude oil, that impulse line can get clogged with gunk. If it clogs, the pressure gauge might show a steady pressure, even if the actual process pressure is spiking dangerously.
It becomes blind.
It becomes blind.
That brings us to the end of the source material, and it really changes how I look at these things. We started with a party streamer, a simple paper coil, and we ended up with a liquid-filled, temperature-compensated, bimetallic-corrected precision instrument.
It's a testament to mechanical engineering. These devices don't need electricity. They don't need firmware updates. They rely on the fundamental properties of materials, elasticity, leverage, and fluid dynamics.
They are mechanical computers that have been keeping us safe for over a century.
And they will likely continue to do so as long as we treat them with respect.
I want to leave you with one thought from the source that really stuck with me. We talked about that sludge in the line, the dead space. It makes you wonder, how many pressure gauges in the world right now, maybe in the basement of your building or in the factory down the road, are currently lying to their operators?
A chilling thought. Is it reading 50 psi because the pressure is 50 psi or because the tube is clogged with 10 years of sediment?
On that happy note, go check your tire pressure. Thanks for listening to this deep dive.
Stay curious and stay safe.